First, an identification that looks trivial and is not. An n-tuple can be read as an n-by-1 matrix, called a column vector, or as a 1-by-n matrix, called a row vector. Both are natural isomorphisms, and the book takes the column vector as standard. With that, last episode's scalar equations say exactly this. The output column vector is the matrix times the input column vector. So a linear map between Cartesian spaces becomes left multiplication by one fixed matrix, and map and product coincide. What about functionals? The matrix of a functional is 1-by-n, so a functional is a row vector. Applying it to an input is a row vector times a column vector, giving a 1-by-1 matrix, which is to say a number. Now the adjoint. A functional composed with the map corresponds to that row vector multiplied on the right by the matrix. So with functionals as rows, the adjoint is right multiplication, and transposing back to columns makes it left multiplication by the transpose. Now change of basis. Two bases for one space give two basis isomorphisms, and following one with the inverse of the other changes coordinates into coordinates. Do not confuse it with the map sending the first basis to the second, which acts on the space itself. For this, the book draws a two-story diagram. Both stories are Cartesian spaces. The abstract spaces sit between them. For basis isomorphisms, join them up, and the two changes of coordinates stand at the sides. 9 maps, all constraining each other. The diagram commutes. Any two paths between 2 points are the same map. Pick a pair and read off an identity. The new matrix is the change matrix on the right, times the old matrix, times the inverse of the one on the left. If both ends are the same space, there is one basis change, and the formula becomes a similarity. For functionals, nothing changes on the real line, so their coordinates get the transpose of the inverse change matrix. Compare a vector. The two go opposite ways. For this reason, classical tensor analysis calls functionals covariant vectors and calls the vectors of the space contravariant. Both words recur throughout differential geometry, and their whole origin is those two formulas running in opposite directions. One last thing. The space of matrices has a standard basis, and carrying it across the isomorphism gives a standard basis for the space of all linear maps. The KLTH1 does something simple. It sends the LTH basis vector to the KTH and the rest to 0. Expand a map in that basis, and the coefficients come out on their own as its matrix entries, so the entries were the coordinates in this basis all along. The dual basis is one special case. Section 4 ends here. Next time, trace and determinant.